Welcome to this video series on frequently asked questions about the Java language. In this ongoing series of videos, we'll answer commonly asked questions about the Java programming language. You'll come away from the video with a solution to your question. In the presentation section of the video, we'll provide background information on the topic. Then we'll go into the lab and work out a solution. Next, we'll discuss the solution from an application security point of view. We'll let you know what to watch out for to ensure your code stays secure. Like and subscribe to get more great content like this for free. Ready to get started? Let's go. The question today is, when should you use a linked list over an array list? As a developer, are there times when you should favor using a linked list over an array list, or vice versa, and if so, why? The linked list and array list classes are two different implementations of the list interface. They've been part of the Java language since JDK 1.2 and were introduced as part of the Java Collections framework. One thing to note is that neither implementation is synchronized. Let's look at some of the characteristics of the linked list class. This class is a doubly linked list and is an implementation of the list and DQ interfaces. The doubly linked list simply means that the links between the objects in this list allow us to move either forward or backward through the list with relative ease. Assigning an element is accomplished in linear time, represented in big O notation as big O of n. Big O notation is the measure of the complexity of a function. Linear time, as we have here, means that the complexity of the function increases in direct proportion to the number of inputs. The more data you have, the longer it takes to process. Accessing or inserting in the front or back of the list is a constant, represented by big O of 1. This means the time to perform the operation takes the same amount of time no matter how much data you're processing. As far as memory consumption goes, the linked list generally consumes more space than a similarly sized array list of objects, since the linked list must store additional pointer information. Now let's look at some of the characteristics of the array list. It's a resizable implementation of the list interface. Each array list can grow in capacity as the list gets longer. This is to distinguish it from a Java array, which is fixed. Accessing elements in an array list takes constant time, or big O of 1, so random reads are fast. Adding an element takes at worst O sub n, although adding capacity when the array list size must be expanded to accommodate new list items does add some overhead. In general, the array list consumes less memory than a linked list since it doesn't have the overhead of additional pointers. So which implementation of the list interface should be favored? In general, for any application you create, array list is a better solution. But it depends on your needs and the amount of data you'll manipulate. For smaller data sets, the difference is almost negligible, as we'll see in our coding example. If your algorithm requires you to insert and delete elements in the middle of the list, the linked list will be faster, assuming that you have a list iterator referencing the middle of the list that you can use and maintain, and much slower, as we'll see in our coding example, if you don't. Let's take a look at some code now and see some of the characteristics of the two lists in action. We use IntelliJ IDEA as our IDE. Let's create a class called CompareListPerformance. We'll use the live template PSVM to generate our main method. We'll start by creating two lists of integers. The first one, called ArrayList, will be implemented using the ArrayList class. The second list, called LinkedList, will be implemented as a linked list. And let's create a class-level field called ValueCount and set it equal to 100,000. This number will represent the amount of data that we'll process in each list. Next, let's initialize our lists. We'll create a simple for loop from 0 to value count On each pass, we'll add the value of j to the array list as well as the linked list. Let's add a printf statement to print out the number of values we're testing. We'll use some printf formatting magic to put in the %, $d to format our output with commas, and then 2 %ns to print new lines. And let's add a call to a method called add_to_start and pass in our array list. IntelliJ will generate this method for us. The method will take a list of integers, so we can pass in either the ArrayList or LinkedList implementations to this method. Let's change the argument name to TheList in order to make it nonspecific. And we'll go back to the main method and add a call to the method using LinkedList. Now let's add the code to the add_to_start method. We'll start by creating the timing code. We'll use the java.time.instant class. This class has been around since Java 8 and represents an instantaneous point in time. We'll create a variable called begin and set it equal to now. And we'll create another variable called end and we'll also set it to now. Obviously, the code that does the work will go between these two invocations of now. And we'll print out a message using println and specify the delta time. We'll get the name of the class we're testing at the moment by invoking the getClass and getName methods of the list that we're currently processing. And we'll print out the difference between begin and end using the between method of the java.time.duration class and convert the results to milliseconds. Now let's write some code. In a for loop, which will iterate through value count times, we'll add an element to the beginning of the list and then remove it. Let's go ahead and run that code. In our output, we get a message that says we're running on a large list of 100,000 data elements before we perform the add_to_start operation. Notice in the output, the time taken for the array list is 4,750 milliseconds, or about 4.75 seconds. And the time for linked list is lightning fast at 14 milliseconds. So why the difference? Recall that the array list will grow dynamically, and although it's fast to access, the overhead associated with increasing the size of the list can be substantial. Let's run the code one more time and we see that we get similar results. Now let's add a few more methods to get the timing results for other operations. We'll add a printf statement before the add_to_start call to distinguish those results in our output. Let's add a new printf statement and include the message middle of list. We'll create a new method called add_to_middle. IntelliJ will create an empty implementation of the method. Let's go ahead and add calls to the method using both ArrayList and LinkedList. To save time, we'll copy the code from add to start and paste it into add to middle. Let's rename our argument to the list. We'll update our output message to indicate that we're running the middle test. Otherwise, the output message is fine. And we can keep the add and remove methods as they are. We'll simply divide value count by 2, indicating that we're adding and removing a value to the middle of each list on each pass through the for loop. Now let's copy the add to middle call code in main. And rename it add to end. Once again, IntelliJ has created the method for us, so we simply copy the code from add to middle. Update our printline statement, update our argument, and this time, for the add and remove methods, we'll simply perform the operation at the index value count, which is at the end of the list. Now let's go ahead and run the code and see how each list performs. Here we see the invocations of start of list performed in line with our previous runs of the code. Notice the big difference in time between the two lists operations is in the add to middle method call. ArrayList took 3.874 seconds, while LinkedList took over 18 seconds, or nearly 6 times as long. Notice that for add to end, the times were nearly identical. So the takeaway is, adding to the middle due to the pointer updates can take the linked list significantly longer. So you might be saying, yes, I understand, but I don't have 100,000 items to process. So how might this perform on a smaller list? Great question. Let's take a look. We'll change our value count to 10,000 instead of 100,000. Leave everything else the same and rerun the code. Notice when we do, the add to end method for both lists took less than a millisecond. Add to start for linked list also took less than a millisecond, while ArrayList took 1/2 of 1/10 of a second. And the insert in the middle took longer for the linked list, but only by about half a second. Remember, this is a list of 10,000 items being manipulated, which might be a large amount or not, depending on your application. Now let's run the same code once again, but this time for only 1,000 items. When we do, we see that all the operations took less than a millisecond to perform. So the bottom line is this: data size matters a lot when determining which implementation to use. Armed with this knowledge, you can make a decision that works best for your project. So when it comes to security, are there any issues around the use of ArrayList or linked list? The primary concern is to ensure that the index used to access the data in the list comes from a trusted source and is accurate. Accessing a list outside of its boundary will throw a runtime exception. Should an attacker be able to supply data to your application, They can interfere with the proper operation of your application and cause a denial of service. See the CWEs 1094 and 1057 for more information. Thanks for watching. We hope you enjoyed this video. Please like, subscribe, and share this video with others. Right now, while it's still available, go to www.beginsecuretraining.com to get our free ebook on how to write more secure Java code. When writing code, remember to always begin secure.